Hello, this is mathjazz from Almost Cool, and I am here with more derivative practice problems. Today we're going to be focusing on the product rule and the chain rule. So, here is problem 1. Find the derivative of f of x equals e to the x times sine of 3x. We're going to need both the product rule and the chain rule for this, which will be true, I think, of this problem and the next one. I guess not all of the problems we'll do today, but we will use the product rule and chain rule to do this problem and the next one. So, the first thing, we'll write out the product rule. So we have our derivative is equal to the derivative of our first function times our second plus the first times the derivative of the second. We will recall that the derivative of e to the x is itself, and then we see that we'll need the chain rule for sine of 3x, and the chain rule is, of course, we take the derivative of the outside function, plug the inside function into it, multiply by the derivative of the inside function. So we get e to the x times sine of 3x plus e to the x times cosine of 3x times 3. And pulling the 3 to the front of the second term gives us e to the x sine 3x plus 3e to the x cosine of 3x. Pulling the 3 to the front is purely aesthetic. I think it looks prettier. You might not. Totally unnecessary for the math. I just think it looks prettier. So that's our first problem. Here's our second. Find the first and second derivatives of f of x equals cosine of sine of 3x. This is a three-linked chain. Cosine's on the outside, sine's in the middle, and 3x is on, well, I want to say on the inside, but the middle and the inside sound like the same thing. 3x is the furthest inside. So, I'm going to show a technique. I think I've shown this on a previous video, but this is how I like to organize long chains. I guess 3 isn't very long, but it's helpful. First, you write out all of your functions in a column. Cosine's the outside function, so it goes on top. Sine is the next function, it goes in the middle, and 3x is the inside-most function, so it goes on the bottom of the column. And then we write all of our derivatives for these functions in the next column over. Now the way that this technique works is we start with the top right column. I've highlighted it here, and I've written it off to the side. You start at the top right, and you go down one step and one step to the left, plug that function into your top right function. So here we have sine of x being plugged into negative sine of x. And then from there, we step down until we hit the bottom of the column, plugging in each function as we go. In this case, we only had one function more to plug in, so we have negative sine of 3x. Now, if we had any more functions in our column, we'd plug that, whatever was down here would plug into 3x, and whatever was below that would plug into that function, which we plugged into 3x, and so on. But once we hit the bottom of the column, we stop, we check off negative sine x, and we move to the next function down in the right column, in this case, cosine of x. We start a new list. So cosine of x, we do the same thing with it that we did with negative sine x. We go down one to the left one, and we plug that function into cosine of x. And then we keep plugging in functions until we hit the bottom of the column. We already are at the bottom of the column. The bottom of the column is 3x. So we're done with cosine of x. And we move on to our next function, which is this 3. And we write 3, and we're at the bottom of the right-hand column, so there's nothing to plug into 3. Anyway, after that, we take this third column here that we created by plugging functions into each other, and we multiply everything together. So we get negative 3 sine of 3x times cosine of 3x. This is our first derivative. We are done with the first derivative of our function f. But we were also asked to get the second derivative. Second derivative will be more complicated because now it's not just a chain, it's a chain and a product. So first we use the product rule. Yeah, we use the product rule like so. So our first term is negative 3 sine of 3x. Our second term is cosine of 3x. And so we have our first term times the derivative of our second plus the derivative of the first times the second. And from here, we have our derivatives are each chains. We have the derivative of cosine of 3x, where cosine is the outside function and 3x is the inside function. And we have negative 3 sine of 3x is our other chain, which has negative 3 sine as the outermost function, sine as the next function, and 3x as the innermost function. And we're not going to make the tables for each of these, but we make the tables the same way as we did before. And after doing so, we should get this as our derivative. So the third line is our products that we get after we've made our tables. And our bottom line is what happens when we start combining our coefficients at the front and kind of clean things up a little bit. So at the end we get 9 sine of 3x times sine of 3x minus 9 cosine of 3x times sine of 3x times cosine of 3x. And that's our second derivative. So we now have the first and second derivatives, and that means we're done with the problem. So we move on. This problem is a proof. I mean, all problems are proofs. We're always supposed to prove that our answers are the right answers. That's the power of mathematics, is we can show that we're right. But anyway, so I think these are kind of the more interesting problems anyway. You don't have a specific function you're working with, but you're proving general facts about general classes of functions. So we have to remember what an even and an odd function is, I guess. So here comes the definition of an even function. If we let f be an even function, it has this property. Plugging in a negative x does not change the function. F of x is equal to f of negative x. The definition of an odd function is similar. It's plugging in a negative x changes the function by multiplying it by negative 1. So f of x equals negative f of negative x is an odd function, and we'll get to that. Anyway, this is all we know about our function. I mean, I guess we suppose that it has a derivative. So the two things that we know about this function are just it's even, it has a derivative. So we take the derivative of this equation here. This equation f of x equals f of negative x. We take the derivative of both sides. Doing the same thing to both sides of the equation means we end up with two things that are equal to each other. So this is what we get by the chain rule. The left-hand side, the derivative of f of x, is just the derivative of f of x. And since f is equal to f of negative x, f prime of x is equal to the derivative of f of negative x. By the chain rule, we have that this derivative is equal to the derivative of the outside function, which is going to be f prime, because our function here is f, so its derivative is its derivative. We plug the inside function inside of it, so we get f prime of negative x, but then we have to multiply by the derivative of our inside function, and the derivative of negative x is negative 1. So we get f prime of x equals f prime of negative x times negative 1. And we clean that up a bit to get f prime of x equals negative f prime of negative x, which is the definition of being odd. If a function is equal to the negative of the function with a negative x plugged into it, so g of x equals negative g of negative x, that means g is odd. F prime satisfies this, so f prime is odd. That proves our theorem. Now, the companion problem to this is going to be prove that the derivative of an odd function is an even function. We had an even function before whose derivative we showed was odd. Now we have an odd function, and we're going to show the derivative is even. And it works exactly the same way. We're going to suppose f is an odd function. That means that f of x equals f negative f of negative x. And that means that f prime of x is equal to the derivative of negative f of negative x. By the chain rule, we get negative f prime of negative x times the derivative of our inside function, negative 1. That is, the derivative is negative 1. The function was negative x. And the two negative signs will cancel with each other. This negative sign here and this negative sign here. So we get f prime of x equals f prime of negative x. That satisfies the definition of an even function because our even function definition is g of x equals g of negative x. So f prime satisfies that. It is even. We proved our theorem, and we are done with all 4 of today's problems. So thank you for watching. I hope you're having fun learning calculus. I'm having a great time making these videos. Email your questions to mathjazz9@gmail.com. I'll gladly get back to you and try and answer your problem as best I can. Also check out our website and Facebook page if you feel so inclined. And see you next time. Bye!